vertical and I drop this spool. This is a physical experiment. Or a related experiment, heat treatment of aluminum. They're not going to believe this, but yesterday I went to a seminar about the heat treatment of aluminum. And the guy did not show this movie. All the interesting things you can learn about the heat treatment of aluminum you see in this class, and he did not show it. Okay, so I drop this. The question is the path of the center of the spool off like this, straight down, or swinging off to your left?
Or to the right.
Swinging to your right, swinging straight down, swinging to your left. Okay, quiz clear? Any questions about the quiz? Could everybody just vote E so I know how many people are here? Actually, everybody vote something. Vote something random. Go for it. Random vote. Count to 3. 1, 2, 3, 4. Random vote. Okay. We seal that up. We start a new vote. Okay. Your vote got canceled. Vote again. Okay, 15 more seconds. 1, 2, counting down. 10, 9, 8, 7. Well, I was counting up to counting down. I went 1, 2, waited 3 seconds, and went 10. 9, starting for 15. It makes sense. 4, 3, 14, 15. Okay. See how you voted here? Way to go. See, I'm not always trying to mess with you. Or at least this time, I would say I was trying to mess with you, but you learned something, so that's very nice. So if you draw a free body diagram of this thing, we have this object like so. We cut this thing like so. There's a vertical force here. We cut this like so. There's a downwards force like this. The only forces on this system are vertical forces. It starts out with no velocity. It has an acceleration which is vertical, therefore its velocity is vertical, and that free body diagram stays the same. So long as it stays in that line, the free body diagram doesn't change. And there's nothing to take it off of that line because it starts with 0 position, 0 velocity. Its velocity is straight down. Its position evolving in time is straight down. The free body diagram keeps looking like that. Therefore, the forces keep looking like that. And the acceleration is straight down. So a demo of this is like so. Ready? And the center of mass stays off center. As it falls, the center of mass stays off center, which violates some people's intuitions because you'd like to think, oh, the center of mass is not below the support point, it should swing in, but the only forces are vertical. Why doesn't it swing in? Well, this is not a pendulum. Right? In the pendulum, there's a tension force from here down to the center of mass. Here we have a tension force which is vertical. Now, if we took away this free rolling aspect of it, this would be a different problem because this point would then have an acceleration up in this direction. It would roll around and it would be a very complicated double pendulum kind of motion. Now, if you want to see this one, just to make the demonstration complete and bend up my beautiful movie. Ready? You have to watch it quickly so you can play it back in slow motion. I'm going to go 1, 2, 3, drop so you can turn on the high frame rate. 1, 2, 3, drop. Okay. Now, so for those of you who didn't have slow motion video, it went like this. It went straight down, and this thing stayed vertical the whole time. James has it on video. And you can play it back. You can download it, right? And then play it back in slow motion. Put it into iMovie. take each frame, turn it into 5 frames, so that your friends can play it in slow motion. Okay, any questions about this quiz? Yes? Are we going to do a lot more stuff involving yo-yos? I don't think so, no. What? Can you tell me what is behind that question?
Well, in high school physics, there was a whole period where we were doing rotation, and the teacher responded to yo-yo problems.
And you got sick of yo-yos.
Well, they were very difficult.
They're not difficult. So either they're very difficult, like too difficult, you have to do them numerically, or they're not difficult. I think we don't have a yo-yo chapter in the book, but you should certainly know how to do. For example, you should know how to calculate how this moves in time. That's an easy enough problem. Okay, so now I want to go on. How do I want to go on? Is I want to go backwards. Last class, last Thursday, I did the class in a bit of a rush at the end, made me feel guilty. So I just want to repeat the end of last lecture just because I felt like too rushed. So the problem we have is a cylinder rolling inside another cylinder, and we would like to figure out how it moves. And I'm not going to do the whole problem. I just want to set up sort of the hard parts. How are you going to figure out how it moves? You draw a free body diagram. Then you notice that problem of a cylinder rolling inside another cylinder. So this is a rolling cylinder rolling in a cylinder. That this problem only has 1 degree of freedom. What does that mean? Is if you know, say, the angle theta or the angle phi, you know where the inner cylinder is. So as this moves, we only have to keep track of 1 number and its rate of change. And so in trying to set up the equations of motion, we'd like to write them all in terms of 1 number or its rate of change. So either theta or phi. I think theta is the more natural one because you see that whole big cylinder, and theta is showing the position of that whole big cylinder. So what we need to be able to do is calculate the angular acceleration of that small cylinder and the absolute acceleration, the linear acceleration of the center of mass of that small cylinder. And we'd like to figure that out in terms of theta and theta dot and theta double dot. So our goal is to figure out what's the angular acceleration of this in terms of theta, theta dot, and theta double dot, and what's the linear acceleration of this in terms of those variables. Why do we want that? Because then given this free body diagram, we can write F equals ma and angular momentum balance about this point or any point we like, and we will know how to flesh out that equation and turn it into differential equations. Okay, any question about how we're proceeding? You guys in the last rows behind James, come forward, please. Okay, so the hard part, the technically hard part of this problem is the kinematics, the geometry of motion, that's using the rolling constraint to figure out what is this angular acceleration, or this linear acceleration and this angular acceleration of this inner cylinder. So in order to figure that out, we have to use the geometry of the situation and this rolling constraint. And we have this great equation for the rolling constraint, which is that the velocity of this point is equal to the velocity of this point. When things roll, the 2 contacting points don't penetrate each other and they don't slide, so they have the same velocity. So I can write VC prime equals VC. Sometimes I write this as VC equals VC, like the Laurie Anderson song, let X equals X. So VC prime, this point on this stationary cylinder down here, is 0. So we have 0 is equal to, and then we have the velocity of that point C, which we think of now a different way. We think of it as the velocity of G plus the velocity of C with respect to G. So it's a different way to think about the velocity of this point. It's not still, it's on this moving thing, and it's moving relative to this moving thing. Okay, what is the velocity of G? Well, G is just moving in circles, and we know how to keep track of things moving in circles using polar coordinates. So we're going to use these polar base vectors which change in time as this thing moves along. And the velocity of G is equal to capital R theta dot E theta. And then what's the velocity of C with respect to G? These are 2 points on the same rigid object. all 2 points on a rigid object can do is go in circles around each other. So this is given by omega. And what we mean by omega is omega of the disk, of the inner disk, because the outer disk is still. So this is what I would call omega cross the position of C with respect to G. So that's plugging in 2 general formulas, one in polar coordinates, one about 2 points on the same rigid object. Any questions about that? Now we need to fill this in using variables that we can pay attention to. For example, we have this angle phi. What is the angle phi? This line R is a line which was, I'll put D here, and I'll put a D prime down here. This was the line which was in contact down here at the bottom. So we can keep track of the angular orientation of this thing by how far it's rotated relative to where it was or would be if it was at the bottom. So we have this angle phi that we're paying attention to, and this omega then is minus phi dot k, because we'll always take, when in doubt, the sign convention that counterclockwise is positive for omega. Then we have this r of C with respect to G. What's that? That's little r times E sub capital R. Now we can do this cross product. Here's K crossed with ER. What is K crossed with ER? Well, we look at this picture. We have K coming this direction. We have ER pointed that direction. K towards us, ER in that direction. That's K crossed ER is in the E theta direction. So this turns into R theta dot E theta. Plus, then we have this minus phi dot R K. And, sorry, E theta. Thank you. Professor, why is that EK? Is it that? Okay. Now we can take this expression, and we can take the dot product of both sides of it with E theta, because you can take the dot product of any vector with anything you like. In this particular case, it just pulls out the scalar multiple, and so we have that 0 is equal to R theta dot minus phi dot times R. And then we can put that together to say then that phi dot is equal to minus R over R theta dot. Now this is true for all time. It's not just instantaneously true, because at any instant in time, as this is rolling along, we could find a different C and a different C prime for which this would be true. Do you have a question?
Positive? On that equation?
Yes?
Should be positive.
And this equation should be positive. Thank you. This is true for all time because we can invent points C and C prime at any instant in time. So we can take, even though the points C are changing, this equation is still true. We can derive this again and again at every configuration. Therefore, we can take the derivative, and we can therefore write phi double dot is equal to R over R theta double dot. Or we can write then that omega dot is equal to R over R theta double dot K. So we can write the angular acceleration in terms of theta double dot. Now what about the acceleration of point G? That's easy enough. The acceleration of point G, that's just a point which is going on a circle. So even though it's a rigid object, the point G itself just follows the normal polar coordinate formulas. So the acceleration of point G is theta double dot times R times E theta minus theta dot squared times R times E sub R. And then we can use these to plug into linear momentum balance and angular momentum balance. And I wasn't planning to do the next step. I was going to just leave that as an exercise for you, but I will do it if you want me to. How many people would like me to? Raise your hands. Hi, hi. How many people do not want me to? Okay. What happens if we're going to plug this into linear momentum balance and angular momentum balance? We look at these vectors here, which are pretty well defined. They're directioned by this free body diagram. Let's take angular momentum balance relative to point C. Why do I take angular momentum balance relative to point C? I can use whatever point I want, but let's say I'm trying to find the equations of motion, and I don't care about N and F. I don't know about them. I don't care about them. I get rid of them. How do I get rid of them? Is I find an equation of motion that doesn't contain them, and that equation of motion is angular momentum balance about point C. So I have the sum of moments relative to C is equal to the rate of change of angular momentum relative to C. What are the moments relative to C? All we have is this gravity force. So we have this mg. And I could do the cross product, R cross F, but I can see what the lever arm of that is. The lever arm is just this distance here, which is little r sine theta. And that's positive in the counterclockwise direction. Now, if you don't like what I did here, you can do the cross product and look at the position of G with respect to C and take the cross product of that with minus mgj and work out all the components, and you will get this answer here. Then what's the h dot? For any system, the rate of change of angular momentum is a sum of two terms. One is you think of the whole system as a point mass, and the other is the motion relative to the point mass. For the point mass, we look at the position of G with respect to C and cross it with the mass times the acceleration of G. We always have this term for all systems when we calculate angular momentum, unless we're calculating angular momentum balance relative to the center of mass, in which case we would have a G with respect to G and this term would drop out. And then we have plus the rate of change of angular momentum relative to the center of mass. And for two-dimensional rigid objects, which is all, or almost all we're dealing with in this course, that turns into Ig omega dot k. So that term you have for anything for a rigid object. The first term you have for any system where you're taking angular momentum balance about a point other than the center of mass. Now you want to flesh this out further. So we have our R, M, G sine theta. And then on the right-hand side, we have to fill in these terms here. We have RG with respect to C. RG with respect to C is minus R E sub R. And then we're going to cross that with the mass times the acceleration. And what is the acceleration? It was a R theta double dot E sub theta minus R theta dot squared E sub R. And then we add to that Ig omega dot, which was theta double dot K. Okay, stare at that and tell me if I did something wrong, or if you don't understand how I got there. Yes?
Is there an R over R factor for omega dot?
And there's an R over R factor right here. Is that what you wanted? Any other mistakes or questions? You want to do it out loud? Say again?
You drop your K hat on the left hand side for your dot.
Very good. Why didn't you raise your hand and say that? You get, we're keeping track and we have lecture participation and you get negative points when you understand something and you don't say something. Any other questions or comments? Okay, so now we have to carry out this cross product. On the right-hand side, we have an ER crossed with ER. And as is the nature of these pendulum problems, the centripetal term doesn't show up. There's no angular momentum, rate of change of angular momentum associated with the centripetal acceleration. And that drops out because it's an ER crossed with ER. So we have then ER crossed with E theta, which is a, ER crossed with E theta is a K. That's a positive K. So we have minus R, R, M, theta double dot, K. I'm smelling a sign error here. Plus IG, R over R, theta double dot, K. Now there's a sign error someplace. Let me find out where that sign error is. Now we have phi double dot is equal to R theta double dot, but omega dot had a minus sign here. Because omega going all the way back up to there was a minus phi dot times K. So there's a minus sign in this theta double dot expression. And that shows up then as a minus sign here and a minus sign here. Yes? Yes?
Back in the, for the acceleration, you don't have to put in the R over R in the acceleration like you did in the inertia.
Like I did for the inertia. So why is there an R over R here and not an R over R here?
Yeah.
Okay, so that's the question. And the answer is that the angular momentum, or rate of change of angular momentum, this has two parts, one with the linear acceleration of this point and one with the angular acceleration. The linear acceleration of this point is just given by the polar coordinate formula having to do with capital R on this point. The angular acceleration has to do with how fast this is turning, and that R over R, capital R over little r factor, had to do with how fast this is rotating. Does that answer your question? Yes?
Just looking at the picture, I feel like the phi dot and theta dot relation, why isn't that negative? Because like as theta is increasing in that direction, the rolling of the ball is going like the going in the other direction, isn't it?
I think now I have the signs correct, but let me try and do it for you. Here's the inner cylinder, and here's that line on that inner cylinder, and it's going to roll inside the outer cylinder. So what you see is as theta is increasing, phi is also increasing. Who asked the question? Can you see this table? So theta has to do with this angle, and phi has to do with this angle, and I've marked it here. And as theta increases, phi is increasing. Where's the negative sign is in my definition of theta and phi. I've defined theta to be positive counterclockwise, and I've defined phi to be positive clockwise. So it's true that this is going around this way, and this is going around the opposite way, but my angles have been defined with the negative sign in there. Does that speak to your question?
Yeah.
Other questions? Okay, so now we can take this whole expression here and take the dot product with K, and we have mg sine theta is equal to minus something times theta double dot. And what is that something? It's this R, R, M plus I, G, R over R. And there's a little r over here. And if we want to go a step further than this, we can go theta double dot is equal to something times sine theta. In fact, it's something times g sine theta. And then we have, I can bring the r to the other side there, and I have g sine theta, and I can divide through by m. So then I have r, well, whatever I have. I have g over some mess here, which you can figure out. Okay, any questions? The key is that we're left here with the pendulum equation. So not unexpectedly, this has the same differential equation as a pendulum. Certainly rocks back and forth like a pendulum. It's just that the coefficient of the sine theta is different than for a pendulum. Any questions about this? Okay, so now I wanted to go on to a different example having to do with polar coordinates. And I want to just jump into an example, and then I'll pull out the polar coordinates as I need them. So we've worked with polar coordinates so far for circular motion. Now we want to look at polar coordinates for not circular motion. So the problem I want to do is I want to have a bead that slides on a rod. So here's a rod, and I'm going to take this rod and I'm going to flick it like this, and I'm going to have a bead which is on this rod, and I'm going to flick it, and this bead is going to go like so. So the problem is I take this bead and it goes like this, and I'd like to predict that motion. So it goes pretty fast, and I've got a new version of it. I take my gun and load it up like this, just like the old-fashioned guns. I've got to start it down here a little ways like so, part way down, and then I do the same thing again. So it's do you see where? Yeah. These cannonballs are expensive. We can't just, it's brass. It's not just any old piece of metal. Yeah, thank you. Okay, so the question is, why does it go so fast? Can we calculate that? Can we figure that out? Okay, is the situation pretty clear? Okay, so this one's good. It's carbon fiber, it's light. It's good ammunition. Okay, so I'm going to draw it like it's the bead problem. So we're going to have some motor here, and the motor is my wrist. Just to keep it so that the signs and the things we're used to are the way we like, I'm going to throw it that way across the room. So I'm going to flick it across the room that way. I have this motor. I've got this bead, which is going to sit on this thing. And to keep things simple, let's neglect gravity. So we'll assume that the forces are so big that gravity is not important. And let's neglect friction too. Not that we couldn't do this problem with gravity and friction. It's just the equations we get would be more complicated. We can get the differential equations easily enough, but without gravity and without friction, we're going to get differential equations that we can solve. Let's keep track of this angle here, theta. We've got this mass. We can put polar coordinates here, ER and E theta. Sometimes I use small r, sometimes capital R. Let's keep track of the distance this thing has got from the center. Let's call that little r. And let's have an origin here. If we need it, we can have an I and a J, like so. And let's just say that initially, theta is equal to 0, and so I'll put theta 0 equals 0, and theta dot 0 is equal to, and let's just pick some number, let's just call it omega 0. That's how fast this thing is being flicked. And we would like to know, say, how fast this is going at some point. So when theta is equal to, say, pi, how fast is this going? And maybe we could ask what is r equal when theta is equal to pi? How far along the bead, along the rod has this thing gone? Okay, looks like a mechanics problem, doesn't it? So we should be able to solve this by drawing free body diagrams and writing linear momentum balance, or angular momentum balance, or energy balance. In this case, linear momentum balance is going to work fine for us. So how do we proceed? Let's draw a free body diagram, and let's see what happens when we apply F equals ma. So we have this rod here, and we have this bead on this rod. And what forces are acting on the bead? We cut away gravity, but we already neglected gravity. There's a friction force, but we're neglecting friction. So what force is there between the bead and the rod? Only the contact force, which is orthogonal to the surface where they touch. That surface is along the rod, or along the hole in the bead, or along the edge of the bullet. So that force is in this direction. And we can call it N, and it's perpendicular like that. And in case anybody wants to know, we have here on the side our ER and our E theta, so we can keep track of directions of things. Okay, any questions about the free body diagram? Yes?
So it's only in contact on the side that it's swinging toward?
Presumably it's only in contact on one side. It could be that this had a really tight fit, and there was normal forces in all kinds of directions, but that the friction was very low, and just the normal force was tended to be bigger on one side than the other. So what you mean by this force, as always, is a force which is equipolant, statically equivalent to, mechanically equivalent to the whole distribution of contact forces. If you want to think of it, how would it probably be? It would probably be just touching on one side. So as I flick this like this, it's somehow being pushed that way, it's being pushed that way. Probably the force is only between this part of this rod and the back side of this bead. So where this contact force actually is would probably be at that point, roughly. But there's some whole distribution of forces that this is equivalent to. Does that answer your question? Other questions? Okay, so how are we going to figure out how this thing moves? Well, if we're going to model this as a particle, so let's use a particle model. What do we mean by a particle? It means you neglect all the motion relative to the center of mass. So you just don't pay attention to the fact that there's motion relative to the center of mass. Whether or not it's important, you don't pay attention to it. And now we have linear momentum balance. And what does linear momentum balance says? It says that the sum of all external forces is equal to the total mass times the acceleration of the center of mass. In this case, we just have one little point to think of, is we hardly need the subscript g. So we have on the left-hand side the normal force in the E theta direction, and on the right-hand side we have the mass times the acceleration. And the question is, what do we fill in for the acceleration? And this is now the hard part of this problem. This is the kinematics. How do we use this polar coordinate description to figure out this acceleration? Now we could put in here, it's x double dot I plus y double dot j, and that would be perfectly correct. But not useful. Why not useful is because we have this problem set up with polar coordinates. In order to make use of this, we'd have to calculate x in terms of r and theta. It's r cosine theta. Y in terms of r and theta, r sine theta. And they would have to differentiate twice. And when we differentiated twice, we'd have to take into account that both r and theta are functions of time. And we would get a big formula. It's manageable. You could do it on an exam. But it would be a big, messy formula. So we'd like to make it a little bit easier. And as is the nature of shortcuts, they are usually conceptually harder. So what is the shortcut we're going to take here is we're going to use polar coordinates. And we'd like to look at the polar coordinate velocity and acceleration. And we're going to do a little aside. which is figuring out how to write the acceleration and velocity in polar coordinates for this general motion. So what do we have? We have that the position, and what do we mean by the position? We mean the position of g with respect to O, but we just use this shorthand since we only have one point that we're looking at, and obviously we're paying attention to the position relative to O, so we can save some writing just by putting r like that. And what is that? It's r times e sub r. So the position vector as a function of time is an easy thing. Any vector is a scalar multiplied by a unit vector in the direction of that vector, and that's the same with the position vector. What's nice about this is that unit vector in the direction is the radial polar coordinate unit vector. So now to figure out velocity and acceleration, all we have to do is take the time derivative of this and the time derivative of that thing, first and second time derivative. So velocity now is equal to d by dt of the position. That's always true, whether we're writing in polar coordinates or Cartesian coordinates or any other coordinates you want. So that's equal to d by dt of r e sub r, which is equal then to r dot e sub r plus r e sub r dot. Product rule of differentiation works for the product of scalars and vectors. Look up the product rule in Thomas and Finney or whatever your freshman calculus book. Look at the derivation of the product rule and you see it. The derivation will carry through for the products of scalars and vectors. And for the dot products of two vectors and for the cross products of two vectors. Okay, now r dot is fine because we're paying attention to r as a function of time. ER is fine, that's our base vector. ER dot is problematic, but ER dot, we figured out before, is equal to theta dot E sub theta. One of the key formulas. The rate of change of a unit vector is a vector perpendicular to that unit vector multiplied by the rate at which that unit vector is rotating. So that means we can write the velocity of something in polar coordinates is equal to r dot ER plus r theta dot E theta. And that's a totally intuitive formula. What is the velocity of this thing? It's got one part in that direction, which is the rate of change of radius, and one part in that direction, which is how fast it's going in circles. How fast is it going in circles is r theta dot. So r theta dot E theta plus r dot ER, the sum of those two components is the velocity of this thing. And that will equal, of course, x dot I plus y dot j. It's just a different way of writing it. We'll be back shortly. How many of you, when you watch me erase the board, think, I could do a better job of that. You don't have to admit it. I know if I was watching someone like me doing this, I'd be thinking, I could do a better job. But it wouldn't be true about me because I can only do as good a job as I can do. Now I want to find the acceleration. What is the acceleration? Now I'll just keep the notation simpler. V bar to the t's and the o's and the d by dt's and all that. We have to take the time derivative of that thing we just found, which means we have to take the time derivative of this quantity. What quantity is it? It's this r theta dot e theta minus r, sorry. I'll write it there, I wrote it. It's r dot e sub r plus r theta dot e sub theta, and I need to take time derivative of that whole thing. But all of these things are changing in time, so I have to use the product rule, and in that second term, I have to use the product rule as a triple. Okay, so what does this turn into? It turns into r double dot e sub r plus r dot e sub r dot plus, and now we have to do the product rule triple here, r dot theta dot e sub theta plus r dot theta double dot e sub theta plus r times theta dot e sub theta dot. Did I leave? No dot in that term. Okay, so this is the first term, product rule, second term, product rule. Any questions about that? Now we know that E sub r dot, the rate of change of this unit vector, is theta dot E sub theta. And we know that E sub theta dot is equal to minus theta dot E sub r by the constructions I drew, I don't know, almost a month ago now on the blackboard, or you can see them in the book, or you can look at this E sub theta vector, in this case this vector pointed in that direction, and look at the rate of change. As theta increases, the tip goes from here to here, so E sub theta dot is towards the origin. It's minus theta dot E sub r. And then we can collect terms. And when we collect terms, we get something multiplied by E sub r, and we get something multiplied by E sub theta. What do we get multiplied by E sub r? We get this r double dot term. And what else do we get? We get this E sub r term, which is an r theta dot squared, which is minus r theta dot squared. What do we get in the E sub theta direction? Well, we get this easy term to understand, r theta double dot. That's this term here. And then what else do we have in the E theta direction? Well, we have this r dot theta dot E sub theta, but we also have r dot theta dot E sub theta. We have plus 2 r dot theta dot E sub theta. So this then is the polar coordinate formula for acceleration. And it looks like a little bit of a mess. I'm going to now talk through this so you can understand it. Any questions about the algebra before I talk it through? Problems are kind of this bead on a, too bad this thing shows up now. This one I can't use because it's inside, you can't see it. This is silver on silver, but I got to use it. So all problems are kind of this, all polar coordinate problems, and actually any problem you can think of. There's the radial line, and there's the angle of the radial line. And we want to think about the acceleration of this thing. And what we find is the acceleration has 4 terms, 3 of which are easy to understand. Let's look in the radial direction. If this thing is not rotating at all, there's a radial acceleration, r double dot times E sub r. That's easy. It's accelerating in that direction if this thing's not rotating. That's the first term. On the other hand, if this thing is just stuck and this is spinning in circles, this is accelerating because it's always the velocity is always changing towards the center of the circle. There's a centripetal acceleration. That's the minus r theta dot squared in the e sub r direction. That's the second term over there. If this bead is just glued to this rod, and this rod's angular velocity is changing, it's like a car driving on a racetrack in circles, faster and faster. Theta dot times r is how fast it's going. Theta dot times r is its acceleration. So it's an acceleration in that direction due to the fact that the speed is changing. So that's the first three terms. The hard term to understand is that fourth term, which has a special name. It's called the Coriolis term. And it's hard to understand because it's got a 2 in it, amongst other reasons for why it's hard to understand. So what is that term about? It's got two origins. One of them is that there was a velocity in the radial direction, and that velocity in the radial direction changes as this rotates, because here's one radial direction, here's the next radial direction. So there's an acceleration in that direction, which is due to the change of the radial velocity. On the other hand, this thing is kind of going in circles, and it's going in circles at a bigger and bigger radius. So there's a change in velocity in that direction due to the radius of the circles getting bigger and bigger. And those two effects is what gives you that 2 over there. Two effects. One comes from looking at the radial velocity changing in time, and the other effect comes from the circumferential velocity changing in time. Radial velocity vector changing in direction, the circumferential vector changing in magnitude. Those give you those two effects. Okay, now we have this acceleration formula. Now we go back to our example. So our example, we had f equals ma. And now we'd like to substitute in as n e theta is equal to the mass times the acceleration. And now the acceleration has all of these terms in it. E sub r plus something times e sub theta. The e sub r is r double dot minus r theta dot squared. This e sub theta is an r theta double dot plus 2 r dot theta dot. Let's assume in this problem that theta dot is equal to a constant. And we're going to launch this thing by flicking my wrist at a constant angular velocity. Even though the particle's accelerating, I'm going to rotate my wrist at a constant speed. So that means that this term is going to be 0, because we said theta dot is equal to a constant. This term is not going to be 0. In fact, that term is all important. But even though it's all important, we've got this n over here, which we don't know and don't care about. So just to see what's going on, to try to figure out the motion, let's take this equation here and take the dot product of both sides with e sub r. That gets rid of this term. E sub theta dot with e sub r is equal to 0. So we have 0 is equal to m, and then we have this e sub r dot with e sub r is 1, e sub r dot with e sub theta is 0. So this turns into r double dot minus r theta dot is equal to 0. So then it tells us that r double dot is equal to, I'll get it straight, is equal to theta dot squared times r. This thing we took to be a constant, so then this turns into a constant coefficient ordinary differential equation. Constant coefficient, second order linear differential equation. This one we can solve. This is what we call theta dot 0. This is this constant angular velocity. What's the solution of this equation? The solution of this equation is r is equal to a times e to the theta 0 dot t plus b times e to the minus theta dot 0 t. If you don't know that or know how to guess it or get it figured out, go back to chapter whatever it was where we have differential equations. Make sure you know how to get here quickly by yourself. Okay, so what you find out is this thing progresses exponentially in time. In fact, the dominant term as this progresses is this term. And so we can get from this that r is approximately equal to A times e to the net angle theta. If this goes pi, this turns into e to the pi. That's about e to the 3, and that's about 25. It means that the radius of this thing increases by about a factor of 25 in half a revolution. Actually, that's off by a factor of 2 because this A is not the initial radius, it's only half of the initial radius, which we'll figure out one of the initial conditions. Anyway, this thing increases in speed exponentially, increases in radius exponentially. That's why I put it. Any quick questions? Exam next week. We have too many exams in this class. The exam covers through the homework you're getting it tonight. The exam will probably be a little bit harder than the one you just took. The mean was a little too high. The A+ students had trouble distinguishing themselves from the last exam.